ladies and gentlemen.
So let's talk radian measure. So you're used to measuring your angles in degrees. Using 360 degrees is a whole circle. 360 was picked for a lot of different reasons, none of which have to do with the circle itself. So that's where a new way of measuring angles called radians comes in. So radians are defined by the ratio of the arc length, the length around the circle we want to use, and its central angle of any arc that we pick. So 1 radian is when the arc length is equal to the radius of any given circle. So what does that look like? If we draw a circle and we take a wedge of this, if the arc length, the length along the edge, is the exact same as the radius, then this angle here is 1 radian. So how many radians are in a circle? Well, the circumference of the whole circle, the length of the arc around the entire circle, is 2 pi times the radius. That's the circumference formula, right? Well, if we're defining these radians, if we're defining an angle as the arc length divided by the radius, the arc length for an entire circle is 2 pi r. And we're dividing that by the radius. Well, the radiuses would cancel, leaving us with 2 pi radians is the angle for the entire circle. So let's look at some common conversions to degrees to make more sense of this. Well, if we know that the whole circle is 2 pi radians, or 360 degrees, we can cut both in half. 360 divided by 2 is 180, 2 pi divided by 2 is 1 pi. 1 pi radians is the same as 180 degrees. And we can continue to cut this up into nice angles that we're used to. Some common degree angles that we're used to is 90, 60, 45, and 30. Those come up in right triangles, and the special right triangles specifically. Well, the radian measures would be dependent on how you're cutting the 180 to make those angles. 180 divided by 2 is 90, so 90 is half pi radians, or pi over 2 radians. 60 is a third of 180, so a third of pi radians, or pi over 3 radians, is its equivalent. 45 is 180 cut into 4 pieces, so when pi is cut into 4 pieces, we get pi over 4 radians. And last but not least, if we take the 180 and we cut that into 6 pieces, then we get 30 degrees, so pi divided by 6 is its equivalent. Now, these fractions, it might be easier to think of fractions of a semicircle. So instead of thinking about a whole circle, we know that a semicircle has pi radians. So if I wanted half of this angle would be 90 degrees, or half pi radians, because it's a half of the semicircle. So on and so forth. If we wanted to cut it into thirds, then this angle would be pi over 3. Kind of thing. So if that helps, use that. But 180 degrees equaling 1 pi radians is our equivalence, is our conversion ratio. So let's use it to do some things. First and foremost, you're going to have to get comfortable converting between radians and degrees. Well, if we start with radians, we have 2 options. I'm going to show you 2 different ways to do it. The first way is if we have a pi present. We have a pi here in 5 pi over 3 radians. So pi radians is 180 degrees. This is the same as 5 times 180 degrees divided by 3. Well, we can simplify this. 180 divided by 3 is 60. So it's 5 times 60 degrees, which would be 300 degrees. Something else that you can do if you don't have a pi, or if you have a pi and you just don't want to do the substitution, you could do 5 pi over 3 radians times 180 degrees over pi radians. What does this do? Well, it cancels out the pi, and then you're left with exactly what we had before, which does simplify down to be 300 degrees. Either way works. But you have to use this one. You have to use your conversion fraction. You're multiplying by the same thing over the same thing, but different units, in order to convert if you don't have a pi in your radians. Like if I wanted to convert 1 radian into degrees, I'd have to divide by pi radians, and it doesn't cancel out. You'd actually have to figure that out, probably using a calculator. So let's continue. Let's try going the other way around. So when we go from degrees to radians, there really is only one way. It is taking our degree measurement, timesing it by pi radians, and dividing that by 180 degrees. Now the degrees will cancel, and then we can simplify from here. Well, if I have 120 pi over 180, I notice that both of those are divisible by 10, so we can reduce that. And 12 and 18 are both divisible by 6, giving us 2 pi over 3 radians. Not too bad. Now let's use the radians to actually do some of the stuff that we've done before with degrees. So let's take a look at some of that. Well, we defined radians as the ratio of the arc length to the radius. We said that the angle was equal to the arc length divided by the radius. If I multiply both sides of this equation by r, I get that the arc length is equal to the radius times the angle, the central angle specifically, in radians. Now keep in mind, if we have degrees, we have to use the other formula, the theta divided by 360 times 2 pi r formula. But if we have radians, it actually makes our formula a lot nicer. So let's try this out. A circle has a radius of 8 centimeters and a central angle of 40 degrees. What is the length of the arc cut out by this angle? So first and foremost, let's convert degrees to radians. So we have 40 degrees, and we're going to multiply this by pi radians over 180 degrees. This gives us 40 pi over 180. Both of those are divisible by 10, so we can cancel out those zeros. And both of these numbers are even, giving us 2 pi ninths radians. Now we're going to multiply this by the radius. So we have 2 pi ninths times 8 centimeters. Nothing's going to cancel here. So we're going to end up with 16 pi over 9 centimeters as our answer. So it might look ugly as a fraction, but it's far easier and nicer to keep it as a fraction because we're going to have a decimal that repeats forever, so might as well keep it as the fraction. Let's take this a step further. So we're used to having angles between 0 and 90 degrees, especially for right triangles and our trigonometric ratios, our sines, our cosines, and our tangents. Well, we can actually take this a step further. If we take a triangle, right triangle specifically, and affix one of its vertices, specifically the one that doesn't have the 90 degrees, on the origin, and make one side line up with the x-axis, we can affix a right triangle in this way and draw a circle through the other vertice. And in doing so, we get some special properties. So first of all, this point here would be x comma y, and this point here would be 0, 0. So the sine, if we use our trigonometric ratios, the sine of this angle would be the opposite divided by the hypotenuse, y divided by r. So sine of theta is equal to y divided by r. Cosine would be the adjacent divided by the hypotenuse, so we get x over r. And tangent would be the opposite divided by the adjacent, or y divided by x. And in doing so, we can actually find sine, cosines, and tangents of multiple angles. We can actually take this a step further by focusing more on the circle than the triangle itself. If we say that the positive x-axis is 0 and go counterclockwise around the circle, we can actually get some angles that are larger than 90 degrees or pi over 2 radians for our right triangle, which might sound a little bit weird. But basically, every quadrant would be pi over 2 more than the last, giving us a lovely circle defined for 2 pi radians that we can actually use sine, cosine, and tangent for. And because it's a circle, you can keep going. What if you have a negative angle? If you have negative angles, instead of going counterclockwise, you can go clockwise instead by the same amount. And that means that you can find sine, cosine, and tangent for any angle, even those that are above 90 degrees or below 0 degrees. Let's try some of them out. So here we have, find the exact value of cosine of pi over 6. Now, because they don't give us the degree symbol, the little circle we're used to, this is in radians. So what can you do? You could convert this to degrees. Pi over 6 radians is 30 degrees. So this is equivalent to asking what is the cosine of 30 degrees. And we can figure that out. Remember, for sine, cosine, and tangent, we can use special right triangles to help us. One of the special right triangles was the 30, 60, 90 triangle. So let's draw that. We draw a 30, 60, 90 triangle, and I'm always going to make my triangle look like this now. So whatever this angle is, I'm going to make this angle here. Now if it's larger, I'll show you what to do with that. So 30 degrees, for special right triangles, we know that this would be a 1 to square root of 3 ratio. And cosine of this would be the adjacent divided by the hypotenuse, which is square root of 3 over 2. Now you can do these triangles now, especially if you start thinking in radians without doing conversions. With radians now, because there's 180 degrees in a triangle, and 180 degrees is 1 pi radians, all of the fractions of pi in a triangle should add up to 1 pi. So right angles are pi over 2, and if this is pi over 6, I have a sixth and 3/6, which leaves me with 4/6 left, or pi over 3. This again would give us the same ratios of 1 to square root of 3, but it looks slightly different because we're using radians for our angles. But we still end up with this answer of square root of 3 over 2 as our answer. What if we have something like this? This angle here is larger than 90 degrees. What in the world do we do? Well, I start out by drawing a circle. And I'm going to quarter my circle. Basically, every quarter of the circle is pi over 2. And we want 3 pi over 2's. So we're going to go 1, 2, 3. So here we are going down, but we're not moving left or right. So our x value is 0, and we have a y value. For right now, that y value is not really going to matter. And I'll show you why. Tangent is for a coordinate point, y divided by x. So for this coordinate point, it would be y divided by 0. But Mr. Whaley, you can't divide by 0. Precisely. So this either does not exist, or you could say it's undefined. Either way is perfectly fine, but sometimes with tangent, because you'll end up dividing by 0, you'll have these does not exist or undefined as answers. But you saw what we did is we started at 0, counted up by that many, stopped there, and evaluated that point. Let's do this again, but for something that's going to actually give us an answer this time. Let's try sine of 4 pi over 3. Now, if we're thinking in radians, pi, 1 pi is half a circle. So this is 1 1/3 pi. This is one whole half circle, and then a third more. So if we draw our circle, and we quarter it, we are going 1 whole pi, and then a third of the circle more. So we're stopping here. Now let's make this larger. So this angle here is actually pi over 3. It is 1/3 of pi. This whole half circle here was pi. So if we make a triangle based off of this, we can actually use our special right triangles for pi over 3, which means that this angle is 60 degrees and follows a pattern of 1, 2, square root of 3. Now, look at the orientation of our triangle. If this point here is 0, 0, that means that we're going left 1. So this would be -1, and we're going down square root of 3. So that would also be negative. Now, when we do the sine of this triangle, the opposite divided by the hypotenuse, we'd have negative square root of 3 over 2 as an answer. So because we're taking ourselves outside of the realm of 0 to 90 degrees or 0 to pi over 2 radians, we can actually get negative answers for sine and cosine, which is kind of cool. You can't get that if you just focus on right triangles as they are. But when we affix them to circles, we actually expand our possibilities, which I think is just really interesting. Now, if you have questions about this, please feel free to reach out. But my number one recommendation is going to be practice, practice, practice. Radians are interesting. They're a little weird, and they're different. So if you're not used to them, practice is going to make perfect. You've been using degrees for probably years at this point. So introducing a new way to think of angles is going to change up your system a lot, and it's going to take a little bit of time to get used to. So don't stress about it. Good luck with any practice, and I look forward to seeing you in the next video.